Okay, can you guys hear me? Great. I'm here today from NRK to talk about a project that we've been doing for the last 6 months, and it's about how we automatically trying to categorize articles on nrk.no. My name is Øyvind Holmstad. I'm the team lead of the recommendation team at NRK, and my background is a Master of Science, Computer Science, which I graduated at the Arctic University in Tromsø, and I've worked at NRK for the last 5 years. And the first slide in this type of presentations often used to present the company you're representing. But I guess most of you know NRK from earlier. We are the Norwegian Broadcasting Corporation, and we create a lot of content and a lot of services that most people use every day. Actually, 85% of the Norwegian population interact with NRK somehow every day. I'm working at a department called NRK Medieutvikling, or NRK Media Development. And we are responsible for NRK's internet services. We're around 130 employees. And right now we have around 40 consultants helping us building the internet services. And these people span from everything from backend, front-end test, data scientists, design, team leads, and so forth. So everything you know from a regular software development department. We make 4 main products. What we're going to focus on today is nrk.no, which is the online newspaper. But we also make yr.no, the weather app, and some on-demand streaming solutions like NRK TV and NRK Radio. And the mission of our departments is to ensure that NRK stays as relevant in the future as it is today. And basically that means, like I said, today we reached 85% of the population. We want it to stay that way at this time when the media landscape is changing very much. So what I'm going to talk about today is how we can automatically categorize articles on nrk.no by topic. And the reason, we have many reasons for doing this, but one of them, as I said, I'm from the recommendation team, and categories can be a good way to understand what some content is about, so it can help us do recommendations. For instance, like this, where you can recommend one article about music in the context of another article about music. But categories can also be used to build user profiles, which in turn can be used to give personal recommendations. So for instance, this gentleman here has read some articles, or many articles about football and some about food recipes. So the next time he visits the newspaper, we can give him the freshest article about those topics. And when we started doing this, many people asked me, don't you already have manually tagged categories? Isn't this something an online newspaper should have? And we do have that, but they have some problems. And I'm going to go through those problems to explain you why. Problem number 1 is different purposes. So one of them is to group articles by topics. We have a concept called article collections, where we can collect different articles. And one of the things we use that for is grouping articles by topic, like this. And this is pretty much the articles that the categorization that I want from a categorization to use for recommendations and to use for building user profiles. But we also do other stuff with it. We use article collections to do auto-publishing on content pages. So for instance, on the foreign affair page, Urix, we want every new news piece about foreign affairs to be published on this, we call it underforsida in Norwegian. So we add every foreign affair article into Urix, which is a lot. We also use it to group articles by news event. So for instance, when there was the bombing during Boston Marathon, a journalist created the article collection called Bomber under Boston Marathon and added all new articles about that into that collection. Another one is we group content for external purposes. In this case, there are still companies out there writing TV guides, and they need information about TV programs. So this is a page just for them, so they can read about the newest TV shows on, in this case, NRK1. And of course, there's a lot of other weird stuff which I've made article collection about. And there's one in the top right corner, 1967. I'm not really sure what was the purpose of that one. A lot of stupid stuff. Actually, I found a quote about this. So, if you build a feature for one purpose, which is possible to abuse for other purposes, it will eventually be abused for other purposes. Problem number 2. Duplicate article collections about the same topic. So this is actually a result of having the article collections as free text fields. You need to search it up, and the search feature is really bad. So this is some examples of different article collections. It's about fishing. So, fiskefusk Finnmark, fiskedumping Finnmark, fiskeriforvaltning Finnmark, fiskerinæringa I nord, fisk og havbruk I Nord-Norge, fiskeoppdrett I Finnmark, og fiskeri I Finnmark. So this is different. This is all about the same topic, basically, but we have different collections for it. And there's many more. So, if your application contains a free text field and lacks good search, you will end up with duplicate data entries. And of course, there's a third problem, which is the different levels of abstractions, which is a result of both problem 1 and problem 2. So we have some, like the foreign affairs one, which is extremely wide. It has 11,000 articles. And we have other which is extremely narrow, with less than 10 articles. Actually, 1,200 of our collections have only one article in it, and 4,500 have 5 or less. So they're pretty much useless for doing recommendation. And the last quote, if your feature is abused and your definitions contain duplicates, your data quality will be poor. So basically, the sum of all these problems is poor data quality. So our articles and collections, as they are today, are not fit for recommendations or building user profiles. But the computer can help. It can help us categorize articles. So I'm going to go through a recipe, the recipe that we are using to cook up some categories. But first, I just wanted to talk about some of the Google technologies we use. So this is the first one, Google Bigquery. We're using Google Bigquery. This is Google Bigquery. Bigquery is actually the reason that we've so invested in the Google stack, because we're using Google Analytics to collect information and tracking users. And Google Analytics have an export feature to Google Bigquery. So you get a database with all your Google Analytics events, which is really easy to do queries on. So after we started using that, we started adding other data into Google Bigquery as well. So that's why we also use Cloud Dataflow, which is a stream and stream and batch data processing. We can just submit a job, and Dataflow spreads it across many computers, which does the computation and return a result. We use Google Dataproc, which is cluster computing as a service. You can just create a cluster with Apache Spark or Apache Hadoop installed, submit a Spark or Hadoop job, and it shuts the cluster down. So you only pay for it when you're using it. And we use Google Cloud Storage to store data and objects. So this is my recipe. We're going to go through all of these in turn. First one is to create a corpus. So corpus is basically terminology for a collection of documents. So the nrk.no corpus is every article ever written on nrk.no. And we want to use this as input because, I forgot to tell you, we want to do some supervised learning. We want to supervised learning to learn what categories, what category belong to each article. And for machine learning, you almost always want your observations or your articles or whatever you're doing represented as a number. So all the first steps in this pipeline is about getting a mathematical representation of our articles. And the first step in doing that is actually to create a corpus, which we will later be using to find word embeddings, but we'll get to that. First off, we need to clean the corpus. That's because there's a lot of noise in every article. There's HTML tags and numbers and special characters. There's a lot of words in each article that does not say anything about the topic it's about. So if you have a topic, if you have an article about cross-country skiing, it may have words like jeg, du, vi, det. It's small words which doesn't carry much meaning, so we just remove them. We also do one very simple entity detection. And this is basically to make sure that when you read New York, we want it to read as one token in the corpus. So this is actually pretty stupid, because we just look at words with capital letters which follow each other and add an underscore in between. But it's working, because New York is one token. And that way we can, when you have Anna Solberg and Petter Solberg, you can differentiate between them. So this is an example of a text. It's in Norwegian, of course. On the left, you see the original text, and on the right, you see after the cleaning. And what's interesting is, even though you've removed a lot of words, you can still get the gist of what this article is about. The meaning of the topic is still there. It's just a cleaner representation of it. So this is how we built it. We have every article already stored in Bigquery, and we use Dataflow to read it, to do the cleaning, and we write a corpus file, which is basically one big file with every article in it cleaned, which is stored in cloud storage. And I don't know if you guys over here can see the code, but I'll go through it anyway. So Dataflow is really simple to work with. You can see I've set up a pipeline. It's just first read nrk.no articles. That's just the name of the job. And then you can just add a query, which is the nrk articles SQL. It's just a query as a string. And then Dataflow actually, in parallel, streams every article from Bigquery into different nodes, which do the computation in parallel and extract the corpus, and then we just write it as a result. So this is the main method of that job. Okay, so we're on a quest to find a mathematical representation of an article. When we have a corpus, we can use that to find word embeddings. So what we will do is use the corpus as input to a word embedding algorithm. So the algorithm attempts to find patterns and correlations between words in the corpus. That's what we want to find out, which it basically means it looks for what words are used close to each other in a sentence, in a paragraph, and in a document. And these algorithms are available for everyone to use. They first originated from Word2Vec, which was created at Google. And now now the most advanced one is probably FastText, which is a word embedding algorithm developed by Facebook, which builds on Word2Vec. So how is these words represented? This is a pretty stupid examples in 2 dimensions, but it shows how it works. So word embeddings are vector representations of all words in the corpus. And it makes sure that similar words reside close to each other in the vector space. And when I say similar words, it's not similar because they are synonyms or mean the same thing, but it's because they're used in the same type of context. They're used close to each other in sentences. So in this example, politics and government will lie close to each other because they're often used in the same type of article, and football and Barcelona will reside another place in the vector space. And when you have vectors, you can do math. So you can, for instance, use cosine similarity to measure the similarity between words. And in this example, you can see that politics and government get a large number. And if you find a cosine similarity between politics and football, it's a very small number, because they're far apart. But in the real world, the word embedding is high-dimensional. So when we illustrate it, we often use it in 2 or 3 dimensions, but the embedding is usually 100 or more dimensions. And 100 dimension is the standard parameter to fast text, so that's what we use. But you can experiment with other dimensions to get better results. But actually, it's hard to verify if the word embeddings are right. You can just have to use your human intuition and look at the word vectors and see which actually reside close to each other. So here I've tried to illustrate some words which are close to each other. In the top left, we have some politics. Then we have some cross-country skiing, some football, and some words considering the ocean. Yeah. And we build it using FastText, which is made by Facebook. It's open source, and it actually offers pre-trained models for over 150 languages. And when we started out, we tried to use the pre-trained Norwegian model, but that did not work very well with our nrk.no articles. But it's really easy to run your own. You just need a file with a lot of words in it, and then FastText finds the correlation between words that are close. So this is how it fits into our pipeline. We had from the last one, you saw I wrote the Corpus file to cloud storage. I just read it from there into a process from running on Dataproc. And in this case, we're actually not using Apache Spark or Apache Hadoop in Dataproc. We're just using it to create a cluster, which is really strong machine. One simple machine in that, so it's not really a cluster, but you can start a really powerful machine really fast. And then we just run the FastText executable, write the word embeddings to cloud storage, and shut it down. And here you can see how you can start clusters and submit jobs. So we're starting a cluster, submitting a job. Notice the jar path, which is actually just a jar file residing in Google Cloud Storage. So that's how you start a cluster on Google. You refer a jar file on Google, which is the job. And then you delete the cluster when you're done. Next up, some clusters. Because we have these word embeddings with all our words. Now we're trying to find some correlations between them. And in this simple example, it's really simple to see the clusters. I made a circle around them. It's not that simple in 100 dimensions to see how the clusters are really formed, but for this talk, we'll do it in 2 dimensions. So we have a politics cluster, a cross-country skiing cluster, a football cluster, ocean cluster, some ML down to the left, something about food, down right, something about science, and then there's some strange words down in the middle. And let's call them problematic words, because even though we remove a lot of stop words, there's still a lot of words which are not considered stop words, which don't carry a lot of meaning. They're used across all types of articles, and often using word embedding algorithms, they are placed close together in the space because they're used in the same type of way. In the real system, we have 400 clusters. And I wanted to take a look at some real clusters that we got from running FastText and then doing clustering on it. Oops. Can you read this? Okay, great. So this is cluster number 316, and it's about mountains. So these are all words that have at one point been written in an article on nrk.no. So this cluster is basically about mountains and hiking and going around in the wild. But you can see that they're pretty similar. They're about the same thing. Let's move to the next one. This is another example. It's a football cluster, cluster number 310. So it's a lot of players and some teams. Tippeligamål. Oh yeah, I'm a fan of Tromsø. So. And last one about fishing. So this is often the best way to verify the clusters. You have to look at them and see if it makes sense. In this case, it does, for these 3 clusters at least. But from the same one, we had this cluster, 180, which does not make much sense. And if you're observant, you will see that there's a lot of misspelled words here, like this. It's budget. And what happens here is that this word, this misspelling of budget, it's not used in very many articles. So there's a threshold, actually. So if it's used in 5 or less, it won't be in the word embedding. So this word has at least been written like this 5 times on nrk.no. But that's not enough to find the correlation with these words and other business words. So it's been placed in this strange cluster with a lot of other stuff that doesn't actually carry much meaning if you look at them together. It's not a very meaningful topic carrying cluster. Oops, it's another. Where did it go? Oh, there. And as you notice, the clusters are not assigned name. They just have a number, an ID. We've looked at 316 and 310. But if you look at them, you can give them a name. And we did this using Apache Spark, MLlib, which has a k-means clustering algorithm. It's just a standard clustering algorithm that is basically in every machine learning library out there. And just the same, as always, you read input from cloud storage, you create a job, this time in Google Cloud Data Proc, which runs the algorithm, and write the cluster definitions back to cloud storage. Okay, next up, this is the place where we finally get the mathematical representation of our articles. So, given these articles, I've written 3 very short articles, different meaning. First one is Northug and Klæbo enjoy skiing and fruit. Second one, fishermen prefer swimming fish. And last one, science show that salmon is fish. And we have these following clusters from our example. And then we can match the word in the article with our cluster. So we'll start with Northug and say, yeah, that's from the winter sports cluster. And that's from that strange bad cluster down right. Do the same for every word. And fruit is from the food cluster. And get something like this. So what we've done is map every word in our article to the words in the clusters. And we do the same for sentence 2 and 3. So if you take a look at it, we can actually do something like this. Stack the words on top of each other. And then we can do a little bit of math and get this. So this article is 43% about winter sports, 14% about food, and 43% about something else. And that's a new vector. And that's what we call the article embedding. So this is a mathematical representation of the article that contains information about what topic this article is about. So we can, by just looking at the article, we can see this is about winter sports, and this, and some about food, and something about something else. And we could do the same for the other articles. This is about the ocean, This is about the ocean and science. And we get a lot of vectors. That's great. But we still had those problematic words. We maybe want to clean that up. And one way you can do that is take a look at, just take the cluster and see how much is this represented across a set of articles we know is about different topics. So that's what we've done here. We've taken 50 articles about 50 different topics and seen how much does this cluster spread out. And this is one of those bad clusters with words that don't carry much meaning. And you see that it's mostly evenly spread out across the different articles. In comparison to this, this is an article about fish, or this is a cluster about fish, and you can see there's one article that was really about fish, where this stands out. So this is a good one, this is a bad one. And then we can remove the bad ones. We can just throw it in the trash. Then we get an even better representation of the article. So this is about winter sports and food, and this is only about the ocean, and this is about the ocean and science. So you have better vectors, and now we can do math, and we can compute the cosine similarity again, and see that the skiing one and the ocean one is not very much similar, but the two other one about the ocean and the one about science and ocean has higher similarity. So similar articles have large cosine similarity. So it could look something like this for different articles. This is an example about Listhaug. Maybe it's spread out across the clusters like this, and another article about Listhaug will look something like this. So it's pretty similar. It's not the same, but you can see some correlation between them. That's good. We have successfully embedded the topics mathematically. Just to sum up, similar articles have similar topics, have similar vectors, similar articles are close in vector space, and similar articles have large cosine similarity. So this is a bit more advanced, but still built on the same model. We read some input, do a job, write some output to Google Cloud Storage. So this time we read the word embeddings and the cluster definitions into that Dataflow job, read the articles from Bigquery, and does this computation. I'll show you some code. First, we select each article. Then we just do a map over it. So for each article, we do this, which is basically find the clusters and create a vector out of it. So there's a lot of code missing here, of course, but what we're doing is for each article, we do the cleaning first, like we did for the corpus, because we want to be able to match it against the word embeddings. So we clean the article, and then we do a mapping for each word in the article, find out which cluster it belongs to. And save it. And with this, we're really close to doing what we want to do, create categories. So first, to do some supervised learning, we need to create a dataset. Because if we know what categories we want and have examples of articles in these categories, we can use machine learning to train the computer to understand what categorize articles in each category and assign a category automatically. So the first question we need an answer to is, what categories do we want? So we made a list based on something that's called IPTC in use categories, which is a standard categorization of topics. And it's really narrow. It goes down to, as you can see, art, sculpture, and art and entertainment, which goes to art exhibition, which is about sculptures. And we don't write that many articles on nrk.no about sculpture art exhibitions, so we don't need that as a category. So we just went through this and selected the one we felt were most fitting for the content that we produce. But we also need some examples to match with these categories we wanted. So here we actually could start, we could use the existing article collection we already have, because some of them are useful. As I said, a lot of them is not useful, but some of them can still be used, and some of them are of the type that we need. So we just looked through this list and found the one that matched with the one that we wanted. Yeah, and for some of them like this, we just merged them to create the training dataset. So all these article collections got one label. The result from this was 57 categories. So then we could do this. It took our articles as article embeddings and add a label. Because we know, for some articles, we know what they're about already. And then we have a training dataset we can use for machine learning. So the last step is to run supervised classification with article embeddings. And I know there's a lot of other talks here which go into detail about how you do this part. So I'm not going to talk very much about it. But how it works, you have a labeled training dataset. You add it give it to a supervised algorithm, which creates a category model. Then the next time we publish a new article, you can add that or send that through the category model and get the predicted label. And we built this using R, which provides, among all other possible algorithms out there, multinomial logistic regression. And a big reason that we chose using logistic regression is that it gives a probability for each label. So for every of those 57 categories, we get the probability that the article we gave in belongs to this category. And it sums up to 1. So for one article, perhaps you will get we're 90% sure that this is winter sports, 5%, or actually 90% sure that this is cross-country skiing, 5% sure that this is biathlon, and 4% sure that this is biathlon, and 1% is divided among all other categories. There are some other algorithms that gives you probability as well, like naive Bayes. We tried that one as well, gave worse results. But I guess the biggest question you're sitting with right now is, why did you do it in R? Because all other code I've shown you has been in Scala. And the biggest reason for this is that our 2 data scientists are working in R every day. All analysis is done in R. And for this model, they were doing the fine-tuning, they were working on the data set, trying to get better results. So we did a lot of iterations in R. And the result of a logistic regression is actually just a list of coefficients. It's just some numbers. So it's really easy to write them from a file and then write them to a file and read them into Scala, where we have our API, and use it directly. So, same as always, read something from cloud storage, do the training in R with an R script, and write the resulting model to cloud storage. And R have libraries for reading directly from cloud storage and writing to cloud storage. They have actually really good Google support, so you can do Bigquery queries and do analysis straight into your database, so it's working really fine. So, last step, we have our model. So now we have a job, which is called the nrk.no article classifier. It's just a simple Scala application running on our internal Kubernetes cluster. And when that job starts up, it reads in the word embeddings, the cluster definitions, and the logistic regression model. And all the time, every day, it just listens on a queue for events about articles being published. So when a new article is published, a message goes to this queue, which is read by the classifier, which actually reads the article from the nrk.no API. And then it does everything we talked about. It does the cleaning, finds the word embeddings and the cluster definitions, runs this through, creates the article embedding, sends the article embedding through the logistic regression model, and gets the prediction back. And then we write those predictions to an Elastic cluster we have, which is accessible by the recommendation API. So most of the steps until this point is stuff we don't run very often. That's like a one-time job. You run step 1, 2, 3. That's when we want to recalculate. But this is what's running all the time, every day. And the last slide with Scala code. You can see we start by running the cleaner. It's called a Corpus parser. It cleans. Actually, the text that goes into this is the title and the lead and the body of the article. We find the clusters and creates the article embedding, which is sent into the logistic regression model to predict probabilities. We create an article, which is inserted into Elastic. And that's it. The articles are served. So just to sum up, we use a lot of Google technologies. We use fast text from Facebook. We use Apache Spark to do the k-means clustering. We use R to do the logistic regression. And finally, we use Kubernetes and Elastic to serve it. So a lot of technologies involved to do something seemingly simple. So then what's next? Well, we're still not in production. It's getting really close. We're still not there. But with this automatic categorization, we finally have a uniform article categories on the same level of abstraction. And now it's impossible to create duplicate definitions. It will save some time for the journalist. And the article collections, which are still in use today, have one less purpose to serve, which is good. And of course, the end goal of all this is to be able to build great user profiles, which can be used to give personal recommendations when you're using our services. So that this guy can get articles and also TV programs about winter sports and recipes. And this old lady can get her content about art and aviation and weather. And that's it. If you have any questions, I'll be happy to answer. And you can, of course, come and talk to me after the talk. Thanks.